Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Last couple of classes we have discussed about the advanced functional alloys, and today we will continue that discussion and a new advanced functional alloy today we will briefly discuss, that is high entropy alloys. You may have heard about the terminology entropy while reading in thermodynamics, also on the mixing entropy you have heard. So, in case of several alloy system, we can increase this entropy value or mixing entropy value, and these are the major aspect of a high entropy alloy. So, this high entropy alloy are the composition based definition. It says that 5 or more principal elements with concentration of each element being 35 to 5 atomic percent. Now, the entropy based definition said that the mixing entropy or the magnitude of total molar configuration entropy should be greater than equal to 1.5 R, where R is basically the universal gas constant. Now, let us try to understand by looking at a very simple ternary phase diagram. Here you see a ternary phase diagram, a schematic diagram. So, whenever we develop some alloys, let us say a aluminum alloy, aluminum copper alloys. Okay. So, mostly we took the help of one of these terminal solid solution, and maybe it is mixed with some intermetallic phases in order to improve the strength. Solid solution may have a lower strength, right. And now, if we go far away from these terminal solid solutions and then reach to some of the central alloy phase space, then we can get a larger value of this entropy. So, here the existence of high entropy alloy actually evolve. However, one should remember that there should be 5 or more multi-principal element. A multi-principal element means that all of them has almost equal composition. Okay. Now, if I take a B as an example, even though it is not an high entropy alloy, so let us say 50-50. Okay. Now, for a 3 component system, it is all are 100 divided by 3, right. Now, in case of 5 element system means all of them has 20 atomic percentage. So, A has 20, B has 20, C has 20, D has 20 and E has 20. Now, in such a case, we can simply estimate the total number of such equiatomic composition, and let us say with the total number of principal element. In case of 2, we have only one possibility, A 50, B 50. So, there is only 1. So, 10 to the power 1 number of equiatomic composition you can generate, but in case of 4 it is 10. Okay. So, in this way, if we keep on increasing the number of multi-principal element, it basically follows that n is equal to 100 by x to the power c minus 1. So, you can keep on increasing the number of such composition. So, there is an enormous possibility of getting such huge number of composition in this central space. So, usually the Gibbs free energy are represented with delta J mix is equal to H mix minus T into delta S mix. And so, the configurational entropy, that is the delta S mix, that is the contribution of the total free energy in the alloy with 5 or more major element that stabilizes the solid solution state relative to a multi-phase microstructure. Since here we are talking about evolution of one or phases by due to the presence of multi-principal element. So, that is basically the uniqueness in case of a high entropy alloy. So, the configurational entropy which came from this thermodynamic third principle, third law, you know, that is delta S is equal to K ln W. Okay. So, W is a measure of the randomness. Okay. So, W is basically the number of ways in which the available energy can be mixed or shared with the particles in a system. So, that is a typical definition of the third law. Now, in case of a n number of element system in a random solid solution, in which case let us say I have the ith component, I may have a ith component which has a mole fraction of x I. So, the ideal configurational entropy per mole is basically x I into ln x I. Okay. Now, I multiply with R and the summation of let us say I is equal to 1 to n will give me basically the net configurational entropy, where R is basically represented with the gas constant. So, this is the basic understanding of this high entropy alloy. Now, let us have a look at the different alloys that people have developed so far, and we first need to look at let us say the mild steel. Okay. And then the super alloys we have discussed, right, and stainless steels we have discussed. And if you look at the very traditional engineering alloys, most of them has a configurational entropy less than R. Okay. And for medium entropy, it is in between basically 1.5 R to 1 R. Now, in case of high entropy alloy, this should be greater than 1.5 R. Okay. So, in such a unique cases, we can simply look at how we have reached to these values, and we must need to calculate and let us take a low alloy steel. In case of a low alloy steel, almost we have 90% of iron, and then we may add a little amount of nickel, chromium, manganese, carbon, molybdenum, silicon, sulfur, phosphorus and so on. So, we consider all the presence of different very little amount of element present in a steel, and then we measure basically the value of the delta S mix, and this value will be somewhat in the range of 0.22 R. Okay. Now, in case of stainless steel, let us say 316 stainless steel, where we have a less iron content. However, we may have some high amount of chromium and nickel, which are one of the very major alloying elements, and the values are 1.15 R. So, these are let us say medium entropy alloys as per the definition. Nickel based superalloy 718, here also we have nickel, and then we have we also need aluminum, some amount of titanium. So, the values lie let us say 1.31, and you can see cobalt based superalloy also the values is 1.13, or let us say a typical bulk metallic glass which has zirconium, titanium, copper, nickel, aluminum. Here also we have multi principal element, but these are let us say the amount of other element is less, and you can calculate it is somewhat in the range of 1.3. So, this is as per definition we call it as a medium entropy alloy. But in case of a high entropy alloy like aluminum, cobalt, chromium, iron, nickel, these 5 element they are present almost let us say equiatomic composition, and that is why the compositions are not written. So, the estimated value is of delta S is 1.61 R. So, this is a high entropy alloy. So, from a low alloy steel to stainless steel to nickel based superalloy and cobalt based superalloy, bulk metallic glass, we have discussed all of them actually in this course, and with increasing we reach let us say to a high entropy alloy system, where the configurational entropy is very high. Now, if we look at again the Hume-Rothery's rule for formation of such a solid solution or substitutional solid solution, it has been told that the radii of the solute and the solvent atom should not differ more than 15%. So, they should be less than that. Okay. The crystal structure of two elements must be very much similar, and the valence electron atom must be very similar. Otherwise, if that is differ too much, then we will get basically intermediate phases. whereas the two element should have very similar electronegativity, otherwise ionic compound will form. So, this is one of the very basic rule of formation of solid solution that we have learned earlier. However, in case of these high entropy system or high entropy alloys, people find out that there are some thermodynamic parameter that can predict the formation of such solid solution phases. So, like one is the enthalpy of mixing. So, enthalpy of mixing we can calculate, that is delta H mix is equal to the summation of ith to n, and we have basically delta H mix A B compound, where the delta H mix is the enthalpy of mixing for the binary equiatomic A B alloy. Whereas, the atomic size difference is delta, which is the Ci and Ri are the composition of the atomic radii of the ith element, and R is basically the average atomic radius. We are talking about this R is the average atomic radius and Ri is basically the atomic radii of the ith element, and C is the concentration. So, the net atomic size difference we can estimate, and this value basically lie with 0 to 8.5. Okay. So, in case of the enthalpy, it lies in between, let us say minus 22 to 7 kilojoule per mole, whereas the configurational entropy value is also important in order to get such kind of formation of solid solution. In case of high entropy alloy, the value lies in between 11 to 9.5 joule per Kelvin into mole. Here basically we have multiplied with R. So, some of these important parameters that can assist us to understand these high entropy alloy. At the same time, valence electron configuration so far also shows such kind of interesting behavior, because in some of the high entropy alloy it has been observed that BCC phase solid solution has formed, whereas in some cases we get FCC phase. So, people have calculated their valence electron configuration of very large number of alloys. You see, these are the large number of alloys, and people find out that for a particular valence electron configuration range, we get BCC phases, in some ranges we get FCC phases, and in between, let us say around 7 to 8 valence electron configuration, we basically get the FCC, a mixture of two phase. Okay. But all of them are high entropy alloy, even though the two phase is present here. Okay. Because the entropy is high, all in greater than 1.5 R in all these cases. So, these are some of these interesting feature to explain this high entropy alloy, and people have proposed that there are some core effect because of what high entropy alloys has formed. Even though it is worth to mention that some of the bulk metallic glasses may also has this kind of high entropy effect, means if you estimate the total entropy delta S configurational entropy, that is greater than 1.5. So, R. So, the three very basic core effect is present. The high entropy effect, here we are talking about the mixing entropy, very high mixing entropy that suppress the ordering, especially at higher temperature, and it facilitate the formation of solid solution phases by lowering the Gibbs free energy. So, the higher the delta S mix, because there is a negative term minus T delta S. So, definitely the G will decrease if we simply increase the entropy of the system, and number of phases formed must be less than the maximum number of Gibbs phase rule actually. Now, the second point here, that the severe lattice distortion effect, because once we introduce multi principal element, then we have a high chance that we distort the lattice. So, here the high lattice distortion occurred due to the atomic size difference. Okay. So, I have A, B, C, D 4-5 different types of atom, and they have different atomic radii. Even though we can estimate delta, which is the atomic size mismatch, but differences in the bonding energies, crystal structure, which basically impede the dislocation motion, it can also provide us a good solid solution strengthening. So, different atomic sizes will provide the solid solutioning effect, that is already understood from the very basic metallurgical principle. Now, on the other hand, if we have such very different types of atoms, then it is expected that the diffusion of atoms will be sluggish in nature, because we have to create some extra space, vacancy, or some other site, vacancy site, so that we can get a good diffusivity. So, because of such kind of differences in the sizes, the difference in the local atomic configuration or environment, that also lead to the different bonding and different local energies of the each site, and diffusion rate of each element is high entropy alloy is different. So, diffusion require the coordinated movement, and slow diffusion determine the kinetics. Okay. So, you can think about that in case of metallic glasses, yes, we also have a lower diffusivity in the undercooled melt. However, there is the effect of a cooling rate. Okay. So, we need to achieve certain cooling rate, so that we can get the metallic glasses, and the Tg should be higher in a system, so that we can get a glass. But in this case, we are only talking about the diffusivity in a solid solution. So, in this case, these are the 3 or 4 very major core effect that people think about, and there are very basic characteristic of such high entropy alloys, like we get a very simple solid solution phases, like what we have talked about, like formation of BCC or FCC phases, or a mixture of BCC plus FCC. However, if we go away from those composition, we can also get some lavish phases, and there are some specific utility of it. I will discuss within a minute. Now, the ductile brittle transition temperature could be as low as to 4.2 Kelvin. This is a uniqueness. Not all high entropy alloy shows such effect, but some of the high entropy alloy has shown such. Hardness of solid solution is usually less. However, by making the microstructure finer, by incorporating some second phases, we can also get a very improved hardness like complex alloy phases. However, there is a good thermodynamic stability of the microstructure, because if delta S configuration is very high, thermodynamically delta G could be very low, and so we can get a better thermodynamic stability of the microstructure. Now, it can also sustain a very high strength of 1800 Kelvin. Okay. So, excellent fatigue resistance compared to steel and titanium alloys, superior mechanical properties at room temperature and elevated temperature. Let us first try to see at some of the unique properties in terms of tensile strength with, let us say, the elongation. You all heard about the aluminum alloys. Aluminum alloys has a very low strength, let us say 70 or maximum 100, 200 it can reach, and magnesium alloys. So, after certain precipitation hardening of aluminum alloys, we can reach within this strength level with a moderate plasticity. However, in case of dual phase steel, martensitic steel, complex phase steels, boron alloyed steels, ferritic stainless steel, bake hardened steel, these bake hardened steels are used for car manufacturing, deep drawable steels. Okay. So, they have a relatively lower strength with a large ductility, and so mostly these steels follow a such kind of area or domain. Okay. Whereas, the high entropy alloys you see are almost sitting at the top of any of the conventional steels. So, they have some unique domain of very high tensile strength as well as very high elongation level. So, they are much superior than any of the conventional engineering alloys. And now, if we look at the temperature of different refractory metal base high entropy alloy, they also shows a very high strength in a wide range of temperature than the conventional Inconel or Haynes alloy. These are typical superalloy that we have discussed earlier. So, the superalloy stresses are here and Haynes alloy is here, and so these are the high entropy alloy. So, we can get a much higher strength level with a much higher temperature level. Very similar way many of such high entropy alloys have shown soft magnetic properties. You can see that they have very high level of magnetization value and they have a very low hysteresis level or very low corrosivity level. So, we can use these high entropy alloy also for soft magnetic properties. Corrosion rate is also outstanding compared to our conventional stainless steels. So, these are some of the very interesting properties that we have seen. So, if I compare with these the benchmark values of high entropy alloys, benchmark values means in terms of engineering or functional properties. So, these compared to the conventional engineering alloys, they are much superior, so far it has been reported. So, let us have a look, like these are the high entropy alloys and these are the conventional engineering alloys. We look at the mechanical properties compared to some stainless steel, it has 870 Vickers hardness with 45% elongation, a toughness, fracture toughness of 200 megapascal, okay, compared to any conventional steels with 80 megapascal root meter. So, they are much superior than any of them. Now, the wear resistance of high entropy alloy is also superior compared to these conventional engineering alloys. The corrosion rate of 0.2 MPY, which is much superior than any of the stainless steel. Oxidation resistance is also comparable with the stainless steel. The thermal conductivity, you can see that they have very good thermal conductivity, which is relatively less compared to the engineering alloys, whereas the electrical and magnetic properties are much superior than any of these conventional engineering alloys. So, here we have a saturation magnetization of 1.2 Tesla and Hc is 1400 ampere per meter, which is comparable with the cobalt based alloys, and here this is also another interesting high entropy alloy, which has a permeability level of 100,000, which is much higher than the perm alloys. So, we can achieve much higher level of good functional properties compared to all these conventional engineering alloys. So, we have looked at. So, they have a brighter prospect and we have large opportunities for future application. Now, if we look at the microstructure, as we said that it may contain single phase BCC, single phase FCC, or maybe two phase microstructure is also possible. People have discovered these days. These are very recent literature I have collected for you from 2017. So, in case of a single phase BCC, these are the larger, let us say BCC grain of somewhat in the range of 200 micrometer. We have also some FCC grains here, and so they have yield strength level. FCC has a yield strength level which is lower, whereas in case of BCC the yield strength level is higher, whereas the ultimate strength is close to it. So, it is almost like a brittle like fracture, whereas in FCC we have seen some of the work hardening, okay, from 147 to 413. So, this is like a 48% plastic strain people have observed, and a better improved properties when obtained when people achieve such kind of two phase microstructure. So, like a BCC plus FCC microstructure, in such an alloy system we have a relatively higher strength, also we have a larger ultimate tensile strength with decent ductility. So, along this direction people try to evolve that or people try to make microstructure with two phases, and a new trend has been generated in these days to get basically eutectic alloy based on these high entropy alloys. So, here there is a large development has been done very recently within last 1 and 2 years. People have seen that in such a system like aluminum, cobalt, iron and nickel system, where we get FCC plus a intermetallic B2, which is also a ordered structure. So, such microstructure give a optimum combination of strength, ductility that can be obtained by making such a microstructure which is a eutectic. So, this is a eutectic alloy which is partially cold rolled, and you can see that the strength level is very high actually, right, and it has a very large plastic strain, which usually do not observe in most of the eutectic system. Eutectic system shows very high strength, but not too much plastic strain. So, these eutectic high entropy alloy compared to conventional aluminum alloys are much superior, and it is much easier to form, and so we get basically a mixture of hard phase plus soft phases, and design of such high entropy eutectic alloy concept is achieving a microstructure composed of soft FCC phase. So, the FCC phase gives us the softness of the matrix, and we incorporate some lamellar B2 phase inside those microstructure, which gives us to maintain such a high hardness values or high strength values. So, this is one of the very important example of such functional alloys. Now, in case of these high entropy alloys, there are already some existing application which other alloys cannot replace. So, if you have very high wear resistance, we can use these high entropy bearings. Okay. So, like cobalt, chromium, iron, nickel, titanium, this is also a high entropy alloy bearing. You can see the outer look, or let us say some of the compression mold where the conventional mold does not perform well after some times of use. So, they have a less life than the high entropy alloy. Also, some of the profile hardened comb shape component, you can see the outer features, and they must look superior than the conventional stainless steels. So, the scientists basically think about some of these potential future application in case of engine material, like better elevated temperature strength, oxidation and hot corrosion resistance due to a good sulfidation resistance, coating barrier, and light transport material with a very high toughness. We have seen 200 megapascal root meter toughness we can achieve. So, energy storage material, structural material, and also for cryogenic application, because they have a very the ductile brittle transition temperature can also reach to let us say 10 K. So, in that case we can apply those material for cryogenic application. So, there are enormous possibilities to use these high entropy alloy, and one has to devote those different engineering aspect, and keeping all these things in mind, one can develop such large number of high entropy alloys, and you can see the number of possible if we increase the number of component, we can also increase the number of possibilities of getting a new alloy actually. Now, if we look at so far whatever has been we discussed in these advanced functional alloys, like Heusler alloys, which are one of the very important system we have discussed. So, in this case, in case of these Heusler alloys, we have basically nickel, manganese and antimony system. So, we have L21 structure, C1b structure, even though I told them that these are also complex alloy phases. We have 100% spin polarization, we have larger number of these functional properties, and so on. Also, we have such ferromagnetic shape memory alloy, where there is a austenite to martensitic transformation depending on the application of the magnetic field, which we use as actuator or micro valve. We have discussed about large number of magnetocaloric alloys, which has also a complex structures and monoclinic phases, and they have some unique properties of a large magnetic entropy change, and we can use them as a magnetic refrigeration or heat pump, because depending on the Carnot cycle and which portion we choose, whether to use it as a heat extraction or a magnetic refrigeration, as well as the high entropy alloy we have discussed, where we have enormous number of possibilities to achieve a very high strength and high elongation and very good corrosion resistance. These are some of the unique functional properties that we have achieved, and people tried to achieve such kind of two phase microstructure in high entropy alloy by mixing, let us say, the FCC plus Lattice phases. At the same time, all of them fall in the category of these complex alloy phases, and also the quasicrystals, which a cluster is represent the overall structure of a quasicrystal, whether it is decagonal quasicrystal or icosahedral quasicrystals, which also have very high hardness values and relatively low let us say the toughness values, which could be used for hydrogen storage or anti-sticky properties or maybe thermoelectric material. So, these are some of the very unique properties that one can derive out of those advanced functional alloys. So, with this we complete the discussion on advanced functional alloy, and we hope that within next 20 or 50 years there are more number of such functional alloys will be developed. So, with this I express my sincerest thanks to all of you for your active participation and joining in this course. With this, thank you very much.